Hello and welcome to another general chemistry video. Today we will be going over module 11, understanding quantum numbers. So there are four types of quantum numbers. There are N, L, ML, and MS. And these four numbers create what we call a quantum set. And these are just a set of four numbers. So before I actually tell you what N, L, ML, and MS means, I need to go over the Pauli exclusion principle, which basically states that no two electrons have the same set of quantum numbers. Simply put, similarly how each specific element has a unique number of protons, well, a specific electron will have a unique quantum number set. All right, well, that out of the way, let's get into the material. So n is just the principal quantum numbers. It goes from 1 all the way up to as many as we need. And this really just talks about the energy level that the atom resides in. And a simple way you can figure that out is just looking at what row of the periodic table it resides in. If it's on the second row, then typically it's going to be on the second energy level. However, there is a caveat to that. If we are talking about the transition metals or the lanthanide and actinide series, we have to -1 and -2 respectively. Right? So if we're talking about carbon, then N will equal 2. But if we're talking about vanadium, even though it's on the fourth period, we have to subtract 1 because we had to follow that rule, right? And that means even though that vanadium's on the fourth, the N for vanadium would actually be 3, right? And that just talks about the energy level. All right, moving on. For L is just the angular momentum of the number, or the angular momentum number. And this is pretty standard, right? And you can see right here, I have a little chart. S is 0, P is 1, D is 2, and F is 3, right? But what do I mean by S, P, D, F? Now, notice on this periodic table, I have kind of broken up this periodic table into 4 chunks. Now we got the S block, the D block, the P block, and the F block. One thing I want to notice is right here, I've kind of outlined it. You can see that each of these, you can create a pair or a pair of atoms within this, right? So the S has 1 pair, the P has 3 pairs, the D block has 5 pairs, and the F block has 7 pairs, right? And what do I mean by pairs? Well, because electrons want to be paired, they will kind of create, or these electrons pairs will create certain shapes, right? And some of the shapes are the S block, and you can see this S block is kind of spherical. The P block, which is kind of like, they're kind of like dumbbells, and D are reflected dumbbells. F and F stands for funky, right? Because we don't know what the electrons kind of make. They make all these weird funky shapes, right? And so that's a quick way to remember that, but L just stands on what block does it lie on. All right, let's move on. ML is just a magnetic quantum number, and it ranges from -L to +L. So notice we're talking about the D block right here. Let's talk about the D block here. So the D block has an L number of -2, or sorry, 2, right? And notice how the ML can range from -2 all the way up to +2. And we can kind of create and split this box into 5 different sections. Why 5? Well, look, notice how many bonding patterns or orbital shapes that we have. We've got 1, 2, 3, 4, 5. Or if you want to be specific, -2, -1, 0, 1, 2, right? And so what the ML just means is what kind of shape or what kind of pair does this reside in? Is it a 0 pair, or is it a 1 pair, or does it look like this? Really, that's what ML stands for, right? And finally, MS is just a magnetic spin. And notice how when we're talking about this, we're talking about pairs, right? So electron pairs. Now, what the 1/2 means is that since we're only talking about one specific electron, it constitutes as 1/2 of the pair. And that's why we have that 0.5 or 1/2. Now, there are positive and negatives because electrons like to have a spin. Now, it can spin counterclockwise or clockwise, and if it spins clockwise, it's positive. If it spins counterclockwise, it's negative, right? And so what do we do with this information? Well, if we take the M numbers, or specifically ML and MS, we can create what we call this orbital box diagram. So say we're talking about an electron that is on the d orbital. Remember that d orbital has a 2. And it also has 6 electrons, right? So we're going to distribute 6 electrons. let's see what we can possibly find out that's on the D and has 6 electrons. Well, 1, 2, 3, 4, 5, 6, let's say iron. Right, so iron has 6 electrons, and we are going to make what we call the orbital box diagram. So notice how, because it's on the D shell, remember that we have 5 different possible shapes that, or bonding patterns that it can find. Well, we can see we set up this box before. Now, we just need to distribute these 6 electrons between these 5 boxes. Now, we do not fill it up 1, 2, 3, 4, 5, 6. We do not fill this up. Why? Because we follow something that we call Hund's rule, Hunds, Hund's rule. And what Hund's rule basically states is that electrons want to be as far away as possible from one another. So we got 1, 2, 3, 4, 5, 6. And this is the correct orbital box diagram for iron. And notice we can see a couple things, right? We can find out that the Ml is equal to -2. Why? Because the last electron that we inputted fell on -2. And is it pointing up or is it pointing down? Well, because it's pointing down, we also figure out that it is -1/2 for the Ms, right? So that's a brief overview of the orbital box diagram, and this is a whole brief overview on quantum numbers. You can pause the video right now if you want to see kind of explore all the shapes of the electron pairs, but for now, I will see you in the next video.